So I was hoping that in the previous video that I put together that there would be enough demonstration there to make a good case that what is happening here is anomalous and it is not explainable by common physical processes such as convection currents, a hot air balloon effect, or buoyancy, or simply the loss of particles of matter by expansion outside of the container. So here I have an analytical balance set up, and that is a piece of styrofoam coated with aluminum foil to reflect away any infrared light that would cause warming, and also to prevent any conduction of heat into the digital scale as well. So I'm just going to demonstrate here by shining this heat lamp onto the setup here that it doesn't cause any change on the readings, as you'll see here, because the foil just reflects the light away and the infrared light as well. So I'm very careful not to shine the lamp onto the front panel of the balance there, because it does actually will actually change the readings too. So now what I have here is a sealable glass container with a thick plastic lid. There is like a rubber membrane around it, and it is designed to be airtight, and it has these clamps on it that keeps that lid on there tight. So this is a very rigid container. It is not going to change its volume, its shape. It's not going to be distorted. And inside there you'll see a piece of cardboard. Just note there it says airtight on the very lid. So there's a piece of cardboard paper in there. It is spray painted black to aid in the absorption of light. So now I'm just going to shine this lamp here on top. And you'll start to see the readings will start to go negative. So that would be 30 milligrams, 40. So that would be weight lost if you measure it in grams, 50 milligrams. So I'm going to get it down about 1/10 of a gram here. And then if I leave it long enough, the weight will eventually come back as the whole thing cools down and the system goes back to equilibrium. And here I just have it at 5 times speed, because it does take a while. So I just want to point out, emphasize the fact that this is quite rigid plastic here. It's not going to bend or flex at these pressures. And here I just put a couple of strips of moist cardboard in there, just to do another slight variation on this. Oh, also note that the now I've flipped the container over, so now it's the glass. The bottom is facing up now, so the light is going through the glass material. you'll see there now it's reading negative 0.05 grams, or negative 50 milligrams. There's a tenth of a gram. Yes, the glass does warm up. But the test I did in the previous video addressed that issue to show that convection currents are not a factor. So that's negative 0.12 grams. And now you'll see here, actually it's not that warm. It's reading 18 degrees Celsius. 20 degrees Celsius, give or take a couple of degrees. So it's not getting that hot. It's not like 80 degrees. So the background surface temperatures are about 10 degrees. And here's 5 times speed. You'll see the weight will slowly come back up towards 0. Background temperature in the room is about 8 degrees Celsius, so it's pretty cool. Now here is a milk jug that's sealed up. I put hot tap water in it, and then what I'm doing is shaking it to cause the jug to bulge out. So I want it to bulge. It's reading about 40 degrees Celsius. So keep an eye there on the readings. I wanted to deliberately bulge it out so that the issue of the balloon concept, I can debunk that. It is not changing a volume that would be enough to account for the difference in weight. So you see there it's actually gaining a little bit. So it's reading 60 milligrams over 0. And that makes sense because when I shook the jug, it caused more warm water vapor to be released into the volume of the jug, and this seems to be the where the magic is. It's where there's the warm water vapor, and the warm water vapor seems to be what's causing the weight loss. And conversely, when it cools down, it causes a weight gain. So you see the gaining there. It's now gained a tenth of a gram because it's sitting there cooling off. So notice the sides they're about they're flat, so they're not bulging or being sucked in any noticeable way. So now there's a little bit of bulge. But look, there's a difference of minus 0.3 grams, 300 milligrams. So in order to account for that by buoyancy, there would have to be an increase in volume of about 1/4 of a liter or 250 cubic centimeters. And I don't think that's the case here. So here is a 4-liter ice cream bucket filled with hot tap water. And I'm going to show this calculation more clearly here so you really get the point. See, there's a little bit of a bulge there from the water vapor pressure inside. It's already showing minus 0.06 grams lost there. So the bulging lid tells me that gas is not escaping. Matter is not leaving the container. So therefore it's not losing weight because it's losing matter. So it's staying relatively flat. The flatness also occurs because it cools down inside and reduces the vapor pressure. You notice there that it says almost there, 0.1 grams. So to calculate how much volume is required to lose that much weight by buoyancy, well, let me do it this way to make the point and make it clear. So the diameter of the lid is 7.5 inches. That translates into 19 centimeter diameter. And according to pi r squared, to get the area would be 272 square centimeters. And then if I just assume that there would be a maximum displacement of 5 millimeters on the lid, or half a centimeter, then I arrive at a volume of 136 cubic centimeters, or 136 milliliters. This translates into a displaced weight of air of 0.163 grams, or 163 milligrams. Looks like we're already well past that. And that's based on the published value of 1.2 grams per liter at sea level, which is where I'm at right now. Now what you see here is a sealable Ziploc bag with a piece of cardboard paper inside. I blew air into there and filled it so it bulges out, and sealed it. So the purpose of that is to show that that is not going to cause a balloon lifting effect due to its expansion, because it's already expanded. So here you will see a slight reduction in weight now as I shine the lamp, and the energy is absorbed on the surfaces of the egg carton paper in there. And also you'll see that the bag retains its shape, its volume. Clearly there's no significant leakage. And weight continues to be lost. And now I speed up the camera, so you'll see a slight return to balance here as I turn the lamp off. And energy is lost from the system. It goes back to equilibrium. So I hope that clears up some of those objections and makes more sense. Or maybe not. Now another important case here is what happens with, in this situation, with the container removed altogether. So now there's no so-called balloon envelope. In this segment, if you have the patience to watch through it, you'll see this piece of cardboard lose multiple grams. I'll speed up the footage to 5 times so you can see it more clearly. So it started there at 10 with a slider at 10. Now it's been moved down to 5 to get balance. So that means it's lost 5 grams. You can already see here it's starting to come back a bit. So in my opinion, what is going on here is something to do with the surface absorbing energy and how that interfaces with the atmospheric gases and water vapor very close to the surface. And I would think that the benefits of this is pretty self-evident, so I don't need to explain that. Conclusions. The principle generating lift is not displacement of air. Buoyancy. The calculated lift from the measured ones is far too great to reconcile within reasonable error. The last experiment clearly showed an envelope or balloon is not needed. 2. The principle generating lift is not due to matter or gases escaping the containers. Although I can't guarantee zero losses, we can make a reasonable assessment that given air has a mass of 1.2 milligrams per cubic centimeter, we would notice or hear gases escape. Furthermore, positive pressure inside a container may open a lid, allowing escape more readily than a negative pressure from the outside would allow or push outside air back in. The reason for this is that the outside air pressure pushes the lid on tighter. My point is, we also saw the weight come back. I'm saying, like a check valve, fluid movement is largely one way only. 3. This principle is not due to outside convection currents dragging it upwards. The demo in the previous video used a plastic barrier right over top of the experiment. This barrier would have inhibited upward air convection velocity. The viewer may notice also that I shone the light downwards onto the egg cardboard inside the large rectangular container, not on the sides. 4. Because the container is not necessary and the lift effect is present, I make the distinction that the cause of hot air rising is rooted in a localized spatial energy density gradient. In other words, the gravitational constant G is modified in what I call hot space. No assertion is made to my awareness that mere hot air has a modified G or gravitational constant associated with it. We are merely taught a density reduction causes buoyancy, or a comparative density change, and so we have lift. Well, there you have it. I'm sure this is still going to cause some brain hurt for some of you. I am not going to convince everybody in these videos. I understand that. And I guess that's just how it is. For someone who is truly a student and really wants to learn, I just suggest that you try the similar experiments yourself and convince yourself. Well, I hope this puts some hot air in your balloon and gives you a lift for the day.